Hello. So, in the last one, we discussed about various properties of statistics, and we discussed about mean squared estimator, mean, median, and a lot of stuff like consistent estimators, how to find them, how to use the Chebyshev inequality, and stuff like that. So, I'm just going to give you a quick recap of what we have discussed, and we are going to move on to something called the maximum likelihood estimation in this one. And we shall see how we use partial differentiation, how we use Lagrange multipliers and stuffs like that. Okay, so let me just write it down. Limit tends to infinity, probability of theta n cap minus theta. Theta is the parameter which theta n cap is estimating, of course. Greater than equal to epsilon is equals to 0. So we say that theta n is a consistent estimator if the following property is satisfied, right? Now obviously we also defined that MSE of theta was simply equals to expectation of theta n minus theta, actually theta n's MSE squared, right? Then we see that if limit n tends to infinity, MSE of theta n equals to 0, then theta n is consistent. This is another property. We can prove it as follows. We see that and this thing here, right here, we can obviously understand that this is less than or equals to the variance and bias, right? So what we can do is as follows. This is by Chebyshev's inequality, but the above thing is just MSE of theta n, right? And this would be 0 because we know that limit of MSE of theta n is also 0. And if that happens, theta n is again a consistent estimator. Now that being said, what we would like to do now is this maximum likelihood estimation. Now, what is a maximum likelihood estimation? Well, obviously, when we have an MLE, we also call it MLE. When we have an MLE in form, what we do is usually estimator for a random sample is given by, so this random sample is given by so this is our maximum likelihood estimator defined, and we do this like this. So we take the product of the PDFs basically, and the PDF is dependent on some parameter theta which we are estimating. So that's how we do it. So we are trying to estimate the probability or the value of theta for which the likelihood is maximum. Okay, so that is what we are going to expect here. Now how do we evaluate this sum? Well, obviously now we turn back to our calculus days and we remember that we can take logarithm on both sides. So and taking the logarithm of this would give us right. And what we can do is we can define this one as, let's say, log of capital L, and log of capital L is equal to this, and we need to maximize log of capital L. So differentiating both sides, we have firstly the question asks us how do we differentiate both sides, right? So well, it's obviously L prime by L, and we are differentiating it with respect to theta, of course. Okay, so since we are maximizing theta, we are differentiating it with respect to theta, and differentiating you get something like this. Comma theta. Therefore L prime is equals to xi theta divided by fxi xi theta, and this is equal to 0. And when this is equals to 0, we can find out certain values of it. So whatever theta we get is called theta mle, which maximizes the likelihood. And we sure would see some example here, and that example would be this. The example is crucial to understanding what we are doing, because otherwise we would never know how to apply it. So the example is, suppose I'll just write down the question first. So we have observed the random sample x1 x2 all the way up to xn, and suppose we have that this xi's belongs to normal distribution of theta 1 comma theta 2, right? So what we need to do here is we need to find out the estimators for theta 1 and theta 2, and we also need to find out the maximum likelihood examples. Okay, so what we need to do here is obviously the PDF for all the xi's given the two estimators theta 1 and theta 2, or the two parameters, is given by 1 by root over 2 pi theta 2 e to the power minus xi minus theta 1 squared by 2 theta 2. Now let us find out the actual value and let us see how do we do it. So the likelihood function, to find the likelihood function, we see this is the expression, right? And with this expression we see that we can write this as product of I equals to 1 to n, and this L is basically the likelihood function which we will be defining now, and well in the upcoming examples as well we are going to use the same likelihood function for x1 up to xn, and it doesn't matter how many parameters are there, we can estimate them all. So this gives us this would be, since the 1 by root over 2 pi theta 2 is a constant independent of I, we see this is equals to 2 pi theta 2 to the power minus n by 2, and the exponentials are all, the product of two exponentials simply adds up the argument, so it's basically exponential of this, right? Now therefore taking the logarithm on both sides, ln of L should be equals to minus n by 2 ln of 2 pi theta 2, not a plus actually, because we have exponential of minus, so exponential and logarithm are inverse functions, so log of exponential is just whatever is the argument, so minus right. Now to find out the expressions and the maximum likelihood expressions for theta 1 and theta 2, we need to do them one by one. So let us start with theta 1. Starting with theta 1, we have, and obviously all the derivative formulas and stuff and integration would be required here, so that would be embedded with this video for your forsake needs. This would be 0, while this would be 2 times therefore this gives us L prime by L equals to minus 2 I equals to 1 to n xi minus theta 1 by 2 theta 2, right? And setting L prime equals to 0, we have we see that summation of I equals to 1 to n xi minus theta 1 is equals to 0. This means that n theta 1 is equals to I equals to 1 to n xi, or theta 1 is just 1 by n I equals to 1 to n xi. Therefore the MLE has been found, and it is 1 by n summation of I equals to 1 to n xi, which is just the sample mean. Now let us do the same method for part 2. Now the first term was minus n by 2 log of 2 pi theta 2. This one would be useful here, and thus we have minus n by 2. Differentiation of log of 2 pi theta 2 is basically 2 pi theta 2 2 pi, and this one the only term here is 1 minus 1 by 2 theta 2, which would be basically minus 1 by theta's differentiation is 1 by 2 theta square. So this term 1 by 2 theta 2, so this minus 1 by theta 2 will only be differentiated, right? And this is theta 2 to the power minus 1, and when differentiated this will become minus 1 to the power theta 2, so basically it's 1 by theta squared. So this would be plus 1 by 2 theta 2 squared I equals to 1 to n xi minus theta 1 whole squared, because this term acts as a constant, right? And therefore L prime by L is minus n by 2 theta 2 plus 1 by 2 theta 2 squared I equals to 1 to n xi minus theta 1 squared. Setting L prime equals to 0, we have Therefore, and this is just sigma square, right? Therefore, we see that theta 1 MLE is just x bar, while theta 2's MLE is sigma squared. And this is how the likelihood is calculated. So we see a lot of examples of differentiation here, and this would always obviously be embedded with it. But then again, we need to practice this more and more so that we get to understand what are the key topics here. Obviously, in the next videos, we shall talk about more about how to do certain distributions and how to do certain things. But before that, you need to watch all the necessary content you need in order to understand all of this stuff. So be sure to clear your basics for integration and differentiation every time, because in every video we've embedded it, and that is required because each one of these videos are equipped with a lot of heavy differentiation and integration stuff, and that is why we have focused so much on integration and differentiation, and we have covered a lot of details in that as well. So I'm just basically writing down what we have done in the last ones so that we understand how to basically come up with the next set of rules and functions for this. So this was the condition for differentiation at the point A. So what we did find was, if we are given a function f from the Euclidean space r to the power n to the Euclidean space r to the power m, we have that if it is differentiable at some a belongs to r to the power n, then there exists a linear transformation lambda which is from r to the power n to r to the power m like this, and the following limit satisfies, that is limit h tends to 0, norm of f of a plus h minus f of a minus lambda of h divided by norm of h goes to 0. So this was the whole definition, and we also found out that lambda is unique, right? So this was our findings for the last session. Now, in this session, we would like to go ahead and prove some more things. So, but for that, we should take a look at how do actually higher dimensional derivatives work. So, if we were to do the following, I'll just write down the question here. Now, we are required to find out the derivative at a, that is we have to find out this quantity, that is the derivative of f at a. Now, notice that whenever you have like a function from higher dimensions, the derivative is not really a single number as in the case of one variable calculus, right? So it's a derivative from r squared to r, and of course this would mean that it's from r to the power 2 to r to the power 1. So the derivative would be a matrix of dimensions 1 cross 2. So whenever you have a function from r to the power n to r to the power m and you find out its derivative, it's always, the derivative is like always, since it's just a linear transformation, the matrix of the linear transformation would be a m cross n matrix. So here it's 1 cross 2 matrix. Now this means just 1 rows and 2 columns. So anyways, we can get to the part easily. We know that sin x's derivative is just cos x, right? Then now if we were to just guess that the derivative of fxy is just cos of x comma 0, we could have done that, and what we can achieve from that is as follows. We can guess the derivative already. That's one way to solve a problem like this. We can already guess the derivative, and then we can use on that to find out our findings. So we can write like this for two-dimensional functions. So it's just like iterated limits, but this works. Now our linear transformation lambda, we want that to be cos cosine of a into x, because at a it's basically cosine of a. So we have limit h comma k going to 0. Now, after this definition, since we know that so this helps us say that, and since also the numerator consists of only real numbers, we can say that the norm is basically the absolute value first of all, and when we have this norm thing here, we can understand that since hk is greater than equal to this should be less than equals to limit h tends to 0 sine of a plus h minus sine of h minus cosine of a into h by mod h. But this is already 0. This is 0 because we know that derivative of sine x at a is basically cosine a, right? So we already know this part. And since we know this part, we can conclude this, since this is less than equals to 0, from like our previous experience, we can say that this modulus is also greater than equal to 0, and thus therefore limit is 0. Therefore, it is easy to say that d of f, what we want to do is ab, so let us do it from ab. So derivative of f at a comma b is cosine of a. That is our answer. Okay. So this completes our problem. Now, it is of paramount importance here that we understand that the rules of one variable calculus sometimes also translate back to this multivariable calculus. That is, we can prove the following. Such that so we are required to prove that if f is a function and f is from r to the power n to r to the power m, and it is differentiable at a belongs to r to the power n, then we are required to prove that it is also continuous at r to the power at a, which is from r to the power n. So this is a direct analog of the property in single variable calculus, which says that if a function f is differentiable at a point a, then it is also continuous at the point A, but it is not necessarily true the other way around, right? Because uh, differentiability is a sufficient condition for continuity, while continuity is just a necessary condition for differentiability. So let us think logically and understand what we can deduce from this. So obviously, let me just write down the given parts first, then we can try and figure out, using all the details we have learned, to see if we can correlate one another. So, well, differentiability at a point in higher dimension means that there exists a linear transformation lambda such that df of a becomes lambda, right? Now, this means that this lambda also satisfies the property that the derivative satisfies. So we can write down now the limit that norm of f of a plus h minus f of a minus lambda of h divided by the norm of h equals 0 as h tends to 0. This is the limit that it satisfies. So it means that the term in the numerator, which is f of a plus h minus f of a minus lambda h, this term is a good approximation, right, to 0 right now. So there is an error term r of h, if we allow it to happen, that when added to the numerator would give us something like this. So firstly, we understand that f of a plus h is quite well approximated by f of a plus lambda h. But if we want to approximate it further, what we can do is we can write, since there exists an error term which is epsilon of h such that f of a plus h minus f of a is equals to lambda of h plus epsilon of h, where limit h tends to 0, epsilon of h's norm divided by this h's norm goes to 0. And this is true, and you can find out that this is pretty much reasonable, and this also forces the above limit. So this error term must go to 0, right? Now from this limit it is pretty much clear that since Now this is a conclusion that we can make, obviously, and this conclusion gives us a way to frame that the error term goes to 0, the norm of the error term goes to 0, right? Now this says, and also if we can prove that the limit for the linear transformation goes to 0 as h tends to 0, we are done, and you will see why. Because now also if h equals to I equals to 1 to n hi ei. Here ei's are the standard basis of r to the power n, that is here firstly hi belongs to r and ei's belong to r to the power n, where ei is just 0 0 1. This is at the ith place, 0 and 0. So this is the standard basis for r to the power n, as we all know from linear algebra. And let us say the vector h is consisting of has this representation, then so that is how lambda of h will be written as. Now using the properties of linear transformation, we can write this as well. So lambda of this basis, right? Now what we can see is that if h tends to 0, then for all I belongs to 1 comma n, hi tends to 0, right? Because when the vector h goes to 0, all of its components go to 0, and therefore limit h tends to 0, lambda of h is simply limit h tends to 0 and this can be written as and this term goes to 0, right? So we have a 0 in total. So this proves that limit h tends to 0, lambda of h is also 0. And together we have proved something very important. Now what we can do is recall that now taking the limit, we have Now this proves that since we have this part, obviously, and both of these limits go to 0, so this is 0, and from this we can conclude that therefore limit h tends to 0, f of a plus h is equals to f of a. This means that f is continuous at a. So differentiability implies continuity. So this was not really the hardest problem, because obviously you understand that this problem here uses the basic definitions and just logical thinking to come to the conclusion that differentiability of a function shall always imply continuity. Okay, and that's not really a hard nut to crack. Now some of these things would require proof and some of them would not, because the first one seems like a pretty easy thing to do, because we can prove the first one as follows. Since f of x equals to y for all x belongs to r to the power n, and we need to prove the derivative is 0, so let us prove it at an arbitrary point h. Limit h tends to 0, f of a plus h minus f of a minus 0 divided by mod h. So this limit should be 0, and we see that limit h tends to 0. Now f of a plus h is y, so is f of a, because it's a constant function, right? And of course with the norms. So this is basically 0 because the numerator has norm 0. So therefore df of a is basically 0, right? Number 2, so since f is the linear transformation here and we want to prove that the derivative is itself, we can say the following limit f of a plus h minus f of a, and this answer should be f of a into h, right? So like this should be the answer that we are looking for, and it shouldn't be f of a into h, it's basically f of h basically. So we can cut this part down, because when you have the function f and the derivative d of f h should be given by f of h. So because that is what we are trying to prove here. But since f is the linear transformation, we see that if you were not clear about this, so there exists a linear transformation lambda h, but we want to prove that the linear transformation is basically the linear transformation that we had before. So starting with the linear transformation, that linear transformation is always differentiable. We have proved that the linear transformation is always differentiable in one of the previous videos. So in this case the answer should be f of h, the derivative should be f of h itself, and we are trying to prove that this limit is 0 so as to establish that fact that the derivative is itself. So we see that since f is a linear transformation, it follows the property of a linear operator. So f of a plus h is basically f of a plus f of h, and we already had minus f of a minus f of h equals to 0, because the numerator is 0. Now well this can again be done, because we see that this kind of problems can be easily done using all the proper things. Now the proof of number 3 should be something like this. Now we know that we can assume that each fi is differentiable at I. So if each fi at A, and we are claiming that the derivative is this, now what we want to prove is that limit is true. Now we can see that f of a plus h minus f of a minus lambda h is basically equal to, now this whole thing can be found out because it's basically a vector now and f as component function. So we can see that the first component is this minus this minus this, second one is this, and similarly the last one should be this, right? Now therefore limit h tends to 0, f of a plus h minus f of a minus lambda h divided by norm of h, this limit then should be equal to norm of we know this vector is basically represented as this, and when we take the norm of that, it's basically a summation but in square root form, but we can, since we have already proved that that is less than equals to the mod of that, so what we can find is this is less than equals to summation I equals to 1 to m fi of a plus h minus fi of a minus dfi of a mod of this divided by mod of h. And we do understand that this, all of this limits goes to 0. This is because since fi's are differentiable at A, so because this is true, we know that limit h tends to 0 fi of a plus h minus fi of a minus dfi of a, which is basically the derivative for fi, divided by mod of h equals to 0 for all I belongs to 1 to m. And that is why this is also true, and this proves that the limit is 0, right? So this is another way of doing it. Now if we are given, let's suppose we can turn our attention to a more simplified problem. I hope we can do that. So let's say if and s of x comma y is basically x comma y, then we need to prove that ds of a comma b is basically s itself. It's basically s itself. Now how do we do that? Well, we see that we can directly find out the limit here. Limit h tends to 0, and let us see the norm, because it will be normally a modulus, because you understand that firstly because the output is always a real number, we can have a real number here. So what we have here is as follows. s of a plus h minus comma b plus k minus s of a comma b, and we are calling the linear operator lambda of h comma k, which is basically s itself. Now we want this limit to be 0, or we want to prove that this limit is 0. So let us see how we can do that. Well, s of a plus h comma b plus k is basically equal to, since s of x plus y is defined like that, so a plus b plus h plus k, this is like minus a minus b, and lambda of h comma k, since we want the derivative is itself, it's basically minus h minus k divided by root over of h squared plus k squared. But this is equal to 0 since the numerator is 0, and therefore it is proved that ds of a comma b is simply s. Let me write down a corollary first. So if f and g are functions from r to the power n to the real numbers and are differentiable at some a belongs to r to the power n, then the following also hold. It proves that the differentiation is also a linear operator, as we already know that differentiation itself is a linear operator, because as we have seen before, the derivative of a multidimensional function is basically a linear transformation which goes from the same dimension to the same dimensions, and that is how we find the answer, right? So in case of summation, it's pretty simple. We can do it plus minus as well. In case of multiplication of two functions, let's say, or composition maybe, so if you are going to multiply f into g, we can write this as g of a into df of a plus f of a into dg of a. So this is how it works. Moreover, if g of a is not equals to 0, we can also define the division as before, like this. We can find g of a whole squared, and we can write g of a into df of a minus f of a into dg of a. So this would give us the rule for the differentiation. So like these are the problems that we are trying to do here, and well, this is something that we would try to understand in the coming lectures on how to find out these properties, how to do them, and things like that. So let us start with a few examples, and we shall see how to do those examples one by one. Example 1. So let f be a function from r squared to r, and we can find that since f is a function from r squared to r and it is defined by f of x comma y, so it's a two-dimensional function given by sine of xy squared. Okay, so find df of a comma b. So we need to find the derivative at the point a comma b. Well, firstly, in this cases we obviously assume that the derivative exists, and we are going to find it by the chain rule, and it does exist because we are just finding a general derivative. We are not really proving differentiability under any condition, and we know that the function sine and the function x and the function y square, all of them are differentiable, and composition of differentiable functions are differentiable as long as they are also in the domain. So this is pretty much how it works. So solution: Now, as we did in chain rule, in this cases, in this kind of scenarios, what we are going to do is we are going to define linear transforms. So first let us define some linear transforms for the sake of this problem and for the others. So what I'm going to define here will be applicable to everything else. So define pi I as the vector 0 comma 0 comma dot 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 I at the ith place and zeros again. Okay, so this is pi I, and also define that pi I prime is basically equals to pi I. This is from the example we did before, that if lambda is a linear transformation, then d lambda is basically equals to lambda. So the derivative of a linear transform is the linear transform itself. So taking that into account, what we can do here is as follows. We are going to define the function f in a certain way. We are going to define it as f of x comma y, which was given as sine of xy squared, and we are going to define this as the composition of sine composed with xy square. We are going to define as pi 1 for x. So we have three variables and we are going to define it as like this: pi 1 into pi 2 squared, and we are going to implement AB, right? So the derivative f dash AB according to the chain rule should be, firstly, inside sine we find out the derivative of sine, and we can find out pi 1 into pi 2 squared. Let me just write it down cleanly, because this wouldn't make much sense if you do not understand it. If I do not write it clearly, it will be of no use. So what I'm trying to say here is we can write it as sine. This is the derivative of sine, and the argument is basically pi 1 into pi 2 squared at the point a comma b, multiplied by, this is the first part of the chain rule where you differentiate the first function and the argument is basically the second function, and now we differentiate the second function, which is pi 1 into pi 2 squared derivative at the point a comma b. Okay, firstly we know that since the derivative of sine is cos, we can simply write cosine and put in the values of a and b. Here it's ab square. So this is the first part, and it is multiplied by pi 1 pi 2 squared derivative at a comma b. Now this is the product of two functions, and we learned how to do them. It doesn't matter because pi 1 pi 2, these are all two-dimensional vectors, but it does not matter because we have learned in the just now that we can do this summations and products and all of these things, right? So what we can do is this: we can find out this as pi 1 prime into pi 2 square at the point ABC, AB, and then again pi 2 squared differentiation multiplied by pi 1 at the point a comma b. This would mean this is cosine of AB squared multiplied by, now pi 1 prime is just pi 1, and this pi 2 squared is basically b squared. You just put in the value b squared, and pi 1 prime is the it's not 0 actually, sorry, it's 1 comma 0. So it's basically pi 1 prime is 1 comma 0 multiplied by pi 2 square, and you put in the value, you get it as b squared, plus pi 2 primes is basically 2 pi 2 into pi 2 prime into pi 1 a comma b. I'm going to do that in the next step. So this is cosine of ab squared, and this is basically b square comma 0 plus 2 pi to pi 1. On putting the value, you get 2ab, and pi 2 prime is simply 0 comma 1, right? Because it's a two-dimensional vector. This is because we have two variables, right, x and y. That is why what we are taking the linear transform, these are two variables. The basis is the basis pi 1 and pi 2 and up to pi n are basically defined by the domain, which is r to the power n. So here the domain is r squared, so we are taking 1. So this becomes cosine of ab squared and same dimensional vectors add up, so we have b square comma 2ab, and if you multiply in the cosine part, what you get is this. You get the answer as b square cosine of ab square comma 2ab cosine ab squared, which is the answer. So in a similar way we can do a lot of other problems, but understand what we did here. This is how it works. Okay, so let us move on to next problem. Example 2. And in the midst of these examples you will see a lot of parts where we are going to remind to you. So in every video, whenever we are doing examples, I'll give you a review of how the chain rule works, and the chain rule video would be included, along with maybe some of the videos from multivariable calculus itself, just to give you a prerequisite, so you can either skip it or you can just revisit it for 10 to 15 minutes so that you understand this part. So what we actually want is, we do not want you to get scattered while watching a particular video, because videos are usually long and they're very much in depth. So these problems which we are solving, they might require a lot of special tools which you might have forgotten, which you might remember. So in case you have forgotten, you can just go back into the same video without changing the video to see whatever you require, and that is how we make sure what to put extra in the video, so that you can go back and check and then come back again. Anyways, so example 2. So this is another example where we have a function from r cube to r defined by x to the power y. So find d of abc. First of all, notice that it has 3 inputs, so the linear transform would be would be 3 dimensional. So all the basis for r cube is 0 0 1, right? 0 0 1, 0 1 0 and 1 0 0. These are the basis operators for the Euclidean space r cube. Now write f of x y z as this. We can write this as x to the power y, which is basically e to the power y log x, which is basically exponential pi 2 into log of pi 1 at the point x y z. So therefore the derivative would be something like this. Firstly, we would be doing exponential's derivative at the point pi 2 log pi 1 at the point a b c multiplied by pi 2 into ln of pi 1 derivative at the point a b c. This would give us, since the derivative of exp is just exp, it's basically e, and if you put in the values of a b c, after that e to the power pi 2 log pi 1 would become e to the power b log a, and what we are left with is this. We are left with pi 2 log of pi 1 prime a comma b comma c, right? This becomes a to the power b, and now this is a product for two functions, so obviously it would be pi 2 prime into ln of pi 1 of abc plus ln of pi 1 prime into pi 2 into abc, right? So this becomes a to the power b, and now pi 2 prime, as I told you, it's 0 comma 1 comma 0, right? ln of pi 1 just becomes ln of a, putting in the value, and this becomes ln of pi 1 prime is just pi 1 prime by pi 1 into pi 2 at the point abc, because ln of x is just ln of f of x is basically f dash x by fx, right? So that's just a single variable calculus task. So a to the power b, multiplying this you get 0 comma ln of a comma 0 plus pi 1 prime is basically 1 comma 0 comma 0, and pi 2 by pi 1, when putting the value, you just get it as b by a. So it becomes on a to the power b, and in bracket it becomes b by a ln a comma 0. And thus, multiplying the constant a to the power b inside the vector, we get the ultimate derivative as a to the power b minus 1 into b, a to the power b into ln a comma 0, which is the answer. And you can check, it's basically a 1 cross 3 matrix, which should be the answer because the function was from r to the power 3 to r to the power 1, right? And it makes sense. Okay, let us do another one. So example 3, given f of x comma y equals to sine of x into sine y, find df at the point a comma b. Well, it again is a two-dimensional function, and let us begin. We can see that f of x comma y can be written as composition of sine multiplied by, now this is something which cannot be written directly, but well, it can be written as pi 1 into sine of pi 2 at the point x comma y for now. So therefore the derivative is df a comma b is basically sine's derivative at the point pi 1 sine pi 2 at the point a comma b, and multiplied by pi 1 sine pi 2 derivative at the point a comma b, right? Well, sine's derivative is cosine, and putting the value you get cosine of a sine b, and this one now pi 1 into sine pi 2 is just a multiplication, so it is basically pi 1 prime into sine pi 2 at the point a comma b plus pi 1 into sine pi 2's derivative at the point a comma b. And these are like relatively simple once you understand the concept, because the derivative of the linear transforms are the one basically giving you the vectors. Okay, here the vectors are like 0 comma 1 and 1 comma 0, and whenever you have something linear transform in a function or itself without the derivative, it is just a matter to put the value inside, the corresponding value inside that, right? It is pi 2, so it should be b, because pi 1 corresponds to a, pi 2 corresponds to b, pi 3 corresponds to c, and so on. So this is cosine of a sine b, and this is basically 1 comma 0 times sine b, right? Similarly, this sine pi 2's derivative is pi 2 prime into cosine of pi 2. So it is basically pi 2 prime into cosine of pi 2, and we also have a pi 1 separately at the point a comma b. This would give us cosine of a sine b. We have sine b comma 0, and pi 2 prime here basically is 0 comma 1, and this is cosine of b into a. So all in all, what we do have is this cosine of a sine b, and we have this as sine b comma 0 plus 0 comma a cos b. Adding them together, we get cosine of a sine b multiplied by the vector sine of b comma a cos b, and multiplying everything together, we get sine b cosine of a sine b comma a cos b cosine of a sine b, which is our answer. So this is a 1 cross 2 matrix, as you can check, which is the answer. So yeah, like these are the questions, and these questions can be solved easily, if not very tough, but well, we would need to do some exercises to solve them. Okay, let's move on to another example to see how this works perfectly. Example 4 given. This one is a bit more complicated, but well, knowing all the rules, I do not think it would be much of a problem to solve them. So this one is sine of x sine of y sine z. Okay, so the first sine bracket closed, second sine bracket closed. We need to find the derivative, of course, at the point ABC. So we can write f of x comma y comma z as the composition of sine with pi 1 sine of this should be pi 2 sine pi 3, right, at the point A comma B comma C. Well, so the derivative is df of A comma B comma C is sine in the point pi 1 sine of pi 2 sine pi 3. So sine 1 into pi 2 sine pi 3, and this is at the point ABC multiplied by pi 1 sine of pi 2 sine pi 3 at derivative at the point ABC. So let us evaluate this first part as in the first sense. It's basically cosine of A sine of B sine C, and multiplied by, let this function be written as g of ABC, g prime of ABC, right? So define g of xyz as, so we are going to define this argument completely differently, x into sine of y sine z. This needs to be removed. Sine of y sine z, right? Now this is basically x multiplied by sine of, we can write it like this, sine of pi 2 sine pi 1 pi 2 sine pi 1, and this could be written in the point A comma B comma C, like that. So anyways, since it's a product of two functions, we can write it as g prime ABC is basically x prime at the point ABC. So it's basically x prime at the point ABC multiplied by this sine of pi 2 sine pi 1 at the point ABC, plus what we can write here is x into sine of pi 2 sine pi 1, this derivative at the point ABC, right? So like this is how this thing works, and we can surely write that in terms of it. So the first one gives us, since x prime is basically pi 1, we can say, because x is basically pi 1. So what we can do is we can write 1 comma 0 comma 0 times sine of b sine a. It was actually z, right? So it should be pi 3 b sine c, plus what we can do is a times sine of pi 2 sine pi 3 whole derivative at the point A comma B comma C. Now let us evaluate this separately. Let us evaluate that sine of pi 1. Is it pi 1? It's pi 2 actually. Pi 2 sine of pi 3, this thing's derivative at the point a comma b comma c, right? What we can do here is as follows. Obviously, using the chain rule, this should be sine derivative of pi 2 sine pi 3 at the point ABC multiplied by, we still have the derivative of pi 2 sine pi 3 derivative at the point ABC, right? Now this is basically cosine of b sine c multiplied by, now pi 2 sine pi 3 would be just pi 2 prime into sine pi 3 at the point ABC plus pi 2 into cosine of pi 3 into pi 3 prime at the point ABC. Okay, so this gives us cosine of b sine c multiplied by, now pi 2 prime is just 0 comma 1 comma 0 into sine c, and this is basically b cos c into 0 comma 0 comma 1. So this gives us the vector 0 comma sine c into cosine of b sine c comma b cos c into cosine of b sine c. So this is what the derivative looks like, and thus g prime ABC would be something like this. Therefore g prime of a comma b comma c would be, so you see 1 comma 0 into sine of b sine c, so it basically is sine of b sine c comma 0 plus, that's the first part, plus you have a into this thing, right? So plus what you have is this 0 comma a sine c cosine of b sine c comma ab cos c into cos of b sine c, and together we have g prime ABC as sine of b sine c comma a sine c cosine of b sine c comma ab cosine of c into cosine of b sine c. This would be g prime of ABC. Now we go back to our original problem. It was cosine of a sine b sine c into g prime ABC. So therefore df of ABC was just cosine of a sine of b sine c multiplied by g prime of ABC, and this would give you the answer as sine of b sine c into cosine of a sine of b sine c multiplied by a sine c into cosine of b sine c into cosine of a sine b sine c comma, and the last part is ab cosine of c cosine of b sine c multiplied by cosine of A sine B sine C, which is the answer. And that would conclude the problem. Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value, and much more. You can also find calculus related calculators like integration, derivatives. There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes we have already explained all the examples, all the problems and theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also, you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel.